So let's see question number 7001. Consider an initial mixture of N2 and H2 gases that can be represented as follows. The gas react to form ammonia gas as represented by the following concentration profile. Label each plot on the graph as N2, H2, or NH3 and explain your answer. This is very easy. I can see that one of them is decreasing. So the one is decreasing most probably is nitrogen, because nitrogen is here and hydrogen is here. Both of them are decreasing, the green one and the blue one. But there is higher concentration of N2. This one is N2, this is N2, and this is N2. H2, there is only two of them. So I can see this most probably is the blue one. So it's low concentration here, but the nitrogen is high concentration here on the y-axis. So this is H2, and it is only two ones of H2 decreasing here, and N2 is decreasing also. But what was not there at the beginning, that can be initially. So this initial mixture, when you started, there is N2 and H2, but there is no NH3 still not yet formed. After some time, it will be formed. So starting from the zero, this is the NH3. So if you want, you can also draw it in the red so you can understand. This is NH3, and it is increasing. At the beginning, it was zero. There is no NH3 here. Then suddenly it starts to form. So zero at the y-axis starts to increase, and then it stops. The increased concentration becomes stable. This is explains the relative shapes of the plot. So I can see this is decreasing, and then at the plateau becomes in equilibrium. So it is fixed, it does not increase. And then H2 and NH3 is the same. When is equilibrium reached? When there is a plateau. So here there is no decrease, here there is no increase, here there is no decrease at this point. At this point, you can see at this point, you can see that there is equilibrium reached. The next question, the amounts of H2 and CO and H2 and CO2 are put in a flask. So they are all placed in a flask. The position corresponds to an equilibrium position. If the CO paste is labeled with radioactive carbon 14, will the carbon 14 be present on this CO only or the CO2 only for a definite period of time? In CO, well, it will be distributed between them equally as the equilibrium is dynamic. So some of the carbon will go here and some will go here, and it keeps making the carbon dioxide and then breaking into carbon monoxide. So it is in equilibrium. So as a carbon monoxide, I can see the atoms of the radioactive carbon in both the reactants and products, not one of them only. The next question is the same equation. If in one experiment, 1 mole of H2O and 1 mole of CO are placed in the flask at the same time and then heated. In a second experiment, instead of starting by putting H2O and CO, I started by putting H2 and CO2. So I started from the products, not from the reactants. Will there be any difference in the composition of the mixture in the two flasks? No, there will be. There will be no difference because it doesn't matter. You start from here, and so you start from H2O. So it doesn't matter if you start from the H2O and reacted with the CO and form the H2 and CO2, and then after that, sometimes there is equilibrium between them. Or you start by placing the container has nothing, you put H2 and CO2, and after some time there is H2O and CO, which is formed after a while. So there is no difference. At the end, there will be equilibrium, and all the reactants will be there with a fixed concentration. Since you started with the same number of moles of these two and the same number of moles of these two, so there is no difference in the quantities as well. The next question, suppose a reaction has an equilibrium constant of K equal to 1.3 multiplied 10 to the power of 8. What does the magnitude of this constant tell you about the relative concentrations of products and reactants? We know that this K is equal to the products divided by the reactants. So it's equal to the concentration of the products to the power of their coefficient divided by the concentration of the reactants to the power of their coefficient. So what does this number tell you? You know that this number is bigger than 1. So the K is much bigger than 1, is to the power of 10 to the power of 8. There is many zeros here. So this tells us that there is very high concentrations of the products relative to the reactants compared to the concentrations of the reactants. So this tells us that a reaction which has a very large K is a very good source of the products. If you have N2 and H2 and NH3 formed, you have to balance this one, so it is 2 and there's 3 here. And if the K is very big number, this means that there is a lot of the products, there is a lot of ammonia. If the number k is very, very small than 1, this means that there are more reactants than products. In our example, we have a very big k, so 1.3 multiplied 10 to the power of 8. So I have here 8 zeros, so this is going to be 1, 3, 1, 2, 3, 4, 5, 6, 7. So this means a very big number, and then since it's a very big number, this means that the product is much more than the reactants. In the next question, we can see the opposite. In the next question, we can see the opposite of the reaction has the equilibrium constant k is equal to 1.7, and this time it is to the power of -8. So this means that this is 8 times moved here. So 8 times moved here means that this is 1, 7, and then there is zeros. There is how many zeros? This is moved 1 time, so it is 1, 0. So instead of 1, 7 becomes like that, and then there is 0, 1, 2, 3, 4, 5, 6, 7. So there is 1, 2, 3, 4, 5, 6, 7, 8, 1 more 0. So this is our number. So this is our number. Like that 1, 2, 3, 4, 5, 6, 7, 8. This is our number. It's a very small number, and since the k is very, very, very less than 1, this indicates that there is a very large concentration compared to that, because k is equal to products over reactants, so products concentration over reactants concentration, and this means that the reactants concentration is much, much, much more bigger than the products, and that reaction which has a very small k like that is a very poor source of the products. If you want the products, it will be very difficult for you to get the products because there is much more concentration of the reactants. For example, that we see here in the solubility, if you have a solubility AgCl, the KSP and this is in equilibrium with the concentration of Ag plus and Cl minus, this is a very low soluble. This AgCl is a solid and the solubility is very low, so the concentration of the ions are very less. Concentration of silver and chloride is very less because it is precipitated down here. It's a white precipitate, and there is no silver or chloride ions. Concentration in the solution is very, very small one. So the product is very less because most of the substance is found in the form of reactants, which is the solid silver chloride, not as a product. So a reaction which has very small k like that is a very poor source of the products because there is very high concentration of the reactant. Question is a little bit difficult question, saying that consider the following reaction at some temperature H2 plus CO. I can see that this is H2O and this is CO reacts to give H2 and CO2. I cannot see any H2 and CO2 because this reaction is initial reaction. We did not start the reaction yet. But when the reaction happens in this equilibrium, we know that the K is equal to 2. How do this problem by trial and error? Try to know when the equilibrium is happening, how many molecules of every one of them is available. Start by trial error like 2. So let's have a look. You are saying that the K is equal to, so concentration of products of over reactants is equal to 2. Let's imagine that, for example, we have 2 molecules of CO has reacted. So 2 molecules of CO has reacted. Where is the CO? So this one has reacted and this one has reacted. And the ratio is 1 to 1 because 2 molecules will react from the CO, so 2 molecules of water will react. Okay, so at equilibrium, there is 2 mole. What are the products? So what are the products? I can see that the reactants are 2 of H2O and 2 of CO. And the products formed, what are the products formed? The CO, so H2O forms 2 of CO. They were not there at the beginning because the ratio is also 2 to 2. And then, because the ratio is 1 to 1 to 1 to 1. So 2CO2 will be formed and 2H2 will be formed. Okay. So when I do like that, how many H2O will be still remaining? Because not all the H2O reacted. I have 1, 2, 3, 4, 5, 6, 7, 8. So I will have 6 unreacted. So I'll have 2 CO2 and 2 H2 and 6 H2O unreacted. So 6 H2O will be there at the end. And I will have also 1, 2, 3, 4, 5, 6 CO, only 2 of them reacted, so 4 CO remaining. This means that this is the ones which is remaining at the end after the equilibrium. So let's try the equation. It tells us that the K is equal to the concentration of H2 multiplied by concentration of CO2 divided by the concentration of H2O multiplied by the concentration of CO. So H2, you said it is 2, and CO2 it is 2, and H2O is 6, and 4 of the CO. So 2 multiplied by 2 is 4, and 6 multiplied by 4 is 24. This is not equal to, this is not equal to 2, so this is wrong. So if 2 and 2 reacted, it is not wrong. Let's try to, if we reacted 3 and 3, it's a little bit long, that's why I'm saying it's difficult. So 3 reacts with 3. 3 reacts with 3. This means that out 3 is formed of CO2 and 3 formed of H2. And out of the 8 water, there is 5 water remaining. And out of the 6, there is 8 water, 5 water remaining. 8 water, 5 water remaining, because at the beginning you have 1, 2, 3, 4, 5, 6, 7, 8, 3 finished, so 5 remaining, and there is 1, 2, 3, 4, 5, 6, 3 remaining of carbon monoxide. So when we make the ratio will be H2 is 3 and CO2 is 3, and divided by the H2O, which is 5, and this is CO, which is 3. So 6, 3 is equal to 9 over 5 multiplied by 3 is 18. So it's equal to half. That's not equal to 2. So this is wrong also. What if I reacted 4 moles and 4 moles? If you reacted 4 moles, so you will get also 4 moles of H2, 4 moles of H2, and 4 moles of H2O, H2 and 4 moles of CO2. And what about the remaining quantities? The remaining quantities, CO2 we have at the beginning, H2O we have 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. 4 of them reacted, so remaining 4 of the H2O, and there is 6 reacted, so 6 reacted from the 6 CO, 1, 2, 4 of them reacted, so 2 remaining, so 2 remaining of the CO. So let's make the multiplication. CO2 multiplied by H2, so CO2 multiplied, we make this twice, so this should be H4H, and this is CO2, so this is CO2 formed, and this is H2O, the reactants and the CO. So the product H2 is 4, and CO2 is 4, and this is equal to 16, and and the reactants H2 is 4, and this is 2, so 4 multiplied by 2 is 8, so 16 over 8, that's equal to 2, and our K is equal to 2, so this is the correct number. So we can say that the answer is that 4 moles of H2O has reacted with 4 moles or molecules, so molecules, because he asked about molecules of CO. This is the correct answer. 4 reacted with 4. Question, consider the following generic reaction. So I will try to consider this reaction where 2A2P gas, the gas is called A2P. It's made from 2 A's and 1 P, and 2 moles of it reacts to form 2 of the A2 and P2. Some molecules of A and P are placed in a 1-liter container. As time passes, the several snapshots of the reaction mixture are taken as illustrated. So this is the reaction. And as time passes, I took several snapshots. So many times I took like pictures of the reaction mixture. And which illustration is the first to present an equilibrium mixture? Explain, and how many molecules of A to P reacted initially. We said the equilibrium is reached, so there is no change in the amount of reactants and products present because the rate of the forward and reaction are equal to each other. The first diagram has how many of A2P molecules? It has, let's count. So A2, it's 2 of the A's, it has 2 of the A's, and 1 P. It has 1, and then it has 2, and then it has 3, and it has 4. So it has 4 of the A2P molecules. And how many of the A2 molecules formed? I have 2 here. So it has 2 of the A2 molecules, and P2 molecules, there is 1. So there is 2 of the A2 molecules and 1 of the P2 molecules found. The second diagram has 2 of the A2Ps. So it has 2 of the A2Ps, same like in our ratio. And it has 4 of the A2 molecules. So it has 4 of the A2 molecules, which is double what we have here. So it has 4 of the A2, which is double what we have here, and has 2 of the P2, which is also double what we have here. So I can say that the second diagram, the first diagram cannot represent equilibrium because there was a net change in the reactants and products. The second diagram is it the equilibrium mixture? It depends on when there is a whether there is a net change between the reactants and products. When going from the second diagram to the third diagram, let's see we contain the same number of type of molecules in as a second. So I can see this is a second, and then this is a third. This is 1, 2. This is 1, 2. So there is a change here, which means that it's not constant. It's not constant. But when after a while when I counted, I see that this is 1, 2, 3. So this is 1, 2, and here I can find also the same 2, and then this is 1, and then this is 2, and then 3 and 4, and it's still here 1, 2, 3, 4, and then I look at this one, I see it's 2, and then I see this is 2. There is no change in the concentration between the second and the third. So this means that when you reach the second one, you already become at equilibrium. So because after that, it becomes constant. So here you reach the equilibrium because it becomes constant. There is no change in the concentrations. So the third diagram contains the same number and types of molecules as the second one. So the reaction initially contained only A2P. So it only contained A2P from the first diagram. 2 A2 molecules and 2 A2 molecules, and 1 P2 is present along with the 4 of A2P molecules. From the balanced reaction, there is 2 A2 molecules, so 2 A2 molecules and 1 P2 molecule formed when 2 AP2 molecules decompose. Therefore, the initial number of A2P molecules present is equal to 4 plus 2 equal to 6 molecules of A2P. Again, I know that the second part is a little bit difficult. How many molecules of A2P reacted initially? You are saying that this is the equilibrium. You are saying that this is the equilibrium. At equilibrium, there is 4 molecules. So this is the 4 molecules of 2A2P. So I can see here, this is the equilibrium. And I have many A2? I have 1, 2. So I have 1, 2, and 2. So I have how many molecules was there initially. So at the beginning, you are saying that there is 2A2P, but here I see 2A2P. So the reaction contained only A2P. It only contained A2P from the first diagram, because I see that from the first drawing there is 2 A2 molecules. Where are the 2 A2 molecules? These are the ones, and 1 P2 molecules present. From the balanced reaction, there is 2 A2s. So instead of 1, 2 here, it becomes 2 A2. So this means that this has not changed. So from the balanced equation, 1 P2 is formed because there is 1 P2 here and it's 2 P2. So when this one was decomposed, when these two were decomposed, they formed 2 P2, 1 P2 molecules. So 1 P2 molecules, so the initial concentration of A2P was 4, and the 2 that's remaining at the end, so it is 6 molecules of A2P. 4 of them has decomposed, so 4 decomposed, and 2 are remaining. Where are they? This is the one remaining, and this is the other one remaining, but there are 4 other molecules which has decomposed initially. Really an important question because it explains what is the difference between K, Kp, and Q. They are all determined, the Q, the K, and the Kp are equilibrium constant determined by the law of mass action. For the K concentration of units of mole per liter, and for Kp, the units are atmospheric pressure. So this is the K and B are the K and the Kp are equilibrium constant. So the K, or sometimes known as Kc in some books, and the Kp for the pressure are the equilibrium constants, and they are determined by the law of the mass action. The Q is called the reaction quotient. So the Q is the reaction quotient, and it is determined by the same way as the K and the Kb, but instead of the equilibrium concentrations, I use only the initial concentrations to find the value of the Q. So when we compare Q to K, when the Q is equal to K, this, or the QP is equal to KP, this means that we are at equilibrium. But if the Q is not equal to K or KB, this means that it is not at equilibrium. If it is bigger, so if it is bigger than it, means it is mainly we are moving towards the left or the backward direction. Or if it is smaller than it, means that we are moving mainly towards the forward direction, with the rate of the forward direction is faster than the rate of the backward. If it's bigger, it means the rate of the backward is faster than the rate of the forward reaction. Consider the following reactions. These two property difference between these two reactions that relate to equilibrium. Let's try to find the K for the first one. So K for the first one is equal to the concentration of HI, which is the product to the power of 2, divided by the concentration of H2, multiplied by the concentration of I2, which is the reactants, which are the reactants. While for the second, the K is equal to the concentration of HI to the power of 2, divided by the concentration of H2. I cannot put the concentration of I because this is solid, not gas. The second difference is that if I try to change the volume, there will be no effect on the first reaction, because when you decrease the size, for example, the pressure will increase. The system will try to decrease the pressure it will move to the direction where there is less number of moles. Here there are 2 moles and 2 moles, so there is no change on the pressure. But here, when I change the temperature, the pressure for the volume, for example, I increase the volume, the pressure will try to let's make the same effect. So I increase the decrease the volume, so the pressure will increase. The system will try to decrease the pressure. So in this case, it will move to the direction of less moles, and here is 1 mole and here 2 moles, so it moves to the left. The concentration of H2 will be more than HI, because there is difference in the number of moles here, 2 moles and 1 mole, because this one is not calculated as it is solid. Solution is very important. For a typical problem, the value of K and the initial reactions conditions are given for a specific reaction, and you are asked to calculate the equilibrium concentrations. Many of these calculations involve solving a quadratic or cubic equation. What can you do to avoid solving a quadratic or cubic equation and still come up with a reasonable equilibrium concentration? We always try to make a good assumption that simplifies the math. In some problems, we can set up the problem so that the net change X must occur to reach equilibrium is small number. This comes in handy when you have expressions like, for example, 0.12 minus x, or 0.727 plus 2x, and so on. When x is very small, we can assume that it makes little difference when subtracted from or added to some relatively big number. So I have a very big number and 1 million, and 1 million subtracted from 1 is nothing. So it's almost equal to 1 million. So I'll imagine like that you have $1 million and I take you $1 from you. So it's you almost, if I ask you how much you have, you tell me I still have 1 million. You will not care about this x which is removed from you. So I can say that 0.12 minus x, that's equal to approximately 0.12, and 0.727 plus 2x, which is very small, is approximately equal to 0.727. If the assumption holds by the 5% rule, the assumption is assumed valid. The 5% rule refers to x or 2x or 3x, etc. That's assumed small compared to some number. If x or 2x or 3x or etc. is less than 5% of the number the assumption was made against, then the assumption will be assumed valid. So if it is less than 5% of the, so it is the original number, so it's compared to some number, it is less than 5% of the number the assumption was made Against them, if the 5% rule fails to work, one can use a math procedure called the method or successive approximations to solve the quadratic or the cubic equation. Of course, one could always solve the quadratic or cubic equation correctly. Exactly, that's generally a last resort and is usually not necessary because we can depend most probably on this 5% rule and get an easier answer to our equation. The next question asking which of the following statements are true, correct the false statement. When a reactant is added to a system at equilibrium, at a given temperature, the reaction will shift right to reestablish the equilibrium. So I have a system which is at equilibrium at a given temperature, and I added a reactant to this system. The reaction will shift right to reestablish the equilibrium. This statement is not true. This statement is false. I will explain everything at the end. But when a product is added to a system at equilibrium at a given temperature, the value of the K for the reaction will increase when equilibrium is established, also is false. So when temperature is increased for reaction at equilibrium, the value of K for the reaction will increase. Also, this is false. When the volume of a reaction container is increased for a system at equilibrium at a given temperature, the reaction will shift left to establish the equilibrium. This is also false. The addition of a catalyst has no effect on the equilibrium position. This is true because it increases the rate of reaction of the forward reaction and the backward reaction, so it does not make a net effect on the equilibrium. So it just reaches the equilibrium more quickly. Statement A is false for reactants that are either solids or liquids. So adding more of this has no effect on the equilibrium. If you have a system which is at equilibrium and at a given temperature, and you have added a reactant, and this reactant is a solid or this reactant is a liquid, it has no effect on the equilibrium. So when a product is added to a system at equilibrium, so you have a product and this product is a product at system at equilibrium at a given temperature, the value of the K for the reaction will increase when the equilibrium is re-established. Imagine I have added a certain product at a given temperature, and these things that the value of the K will increase when the equilibrium is established. I know that if the temperature remains constant, then the value of K is constant. I know the only factor that affects the value of K is temperature. So since we are saying that this is at a given temperature, fixed temperature, then the value of K will never be changed. The value of K will never be changed. When the temperature is increased for a reaction at equilibrium, the value of K reaction will increase. Yes, there is effect of the temperature increase. So temperature is increased for a reaction at equilibrium. Does the K increases or decreases? Let's say why this is false also. So this statement is false because for exothermic reactions, when there is increase in the temperature, when increase the temperature, the reaction will, this is an exothermic reaction, so exothermic is the forward, and you increase the temperature, the system will try to decrease the temperature, so it will move in the backward direction towards the endothermic, which is the backward, so the reactants will become more. So reactants will become more than the products. So this means that the value of K, which is products over reactants, actually the denominator increases. So this means that the value of K is decreased. So the value of K is decreased, not increases. For when the volume of reaction container is increased for the system at equilibrium, the reaction will shift to re-establish equilibrium. So let's imagine that I have reactions that have more reactant gases than the products. It will shift to the left. But if I have it will shift to the left. But if I have more products than reactants, for which more products than reactants, it will shift to the right instead of the left. So let's imagine again, I have 2 here, reactants, and I have 3 products, and you have increased that container volume, so the pressure will decrease, the system will try to increase, so it will move to the right, not to the left here, because there is more products than reactants. If the opposite, then it will move to the left because it will go to the more moles, which is to the left. So it's not always correct.